Hi everyone, it's been a long day for me, but we're gonna whip out one last video for this set. So the last thing we need to talk about is conservative versus non-conservative forces. Conservative forces. Gravity, springs, electromagnetism, of course, that's going to be in the second semester. These are path independent forces. We'll talk about that in a second. We'll look at some examples. We've got non-conservative forces, frictions of all kinds, whatever the friction might happen to be, drag or, whatever, however you want to think about it. Those are all non-conservative. Convenient, theoretical, made-up forces for problems sometimes are conservative, rarely. Depends on how they're done. However, we make these problems up so that we can look at the differences between conservative and non-conservative forces. And we even did theoretical on the board force that varied as a function of x and y. We looked at that and found that it was non-conservative or path-dependent. Okay, so path-dependent forces, if it depends on the path that it takes, then it is non-conservative. And that's about as deep as we're going to go there. Okay, so we've talked about these before, like I just said, somewhat, but this is your official warning, so to speak. This is it, right? We are officially talking about it now. So let's do an example. Let's look at, what do we have? Let's say we have an apartment, and in the apartment, it's 5 floors up. Okay, so there's some stairs. Bing, brr, 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 brr. How many is that? Here's 5, 4, 3, 2, and 1. Okay, so here's our first floor. And we have a couch. Okay, and what we could do is we've got some kind of a pulley winch system, and we could swing the couch out the window and raise it and lower it up and down this way. Okay. Or we can take it up and down the stairs. All right, so let's use our pulley system and call this path 1. And over here we've got path 2. Each of these floors is 3 meters. So we need to go up 3 once, twice, 3 times, 4 times. So our total is 12 meters. All right, and we've got a mass for the couch. That mass is 70 kilograms. Maybe it's a fold out, who knows, it's heavy. The height, of course, we know is 12 meters. And what does that give us for potential energy? So our potential energy, U, is mgh. Okay, put this to memory or stick it on your cheat sheet or whatever, but you got to know this one. mgh. So our potential energy, what is it? Our U in this case would be our 70 kilograms times our 12 meters times our 9.8 meters per second squared. And that's going to end up giving us joules. So our total potential energy is 8232 joules. So if we pushed the couch out the window and just let it drop, no, not letting it happen nice and neatly, that and we don't want to consider air resistance or any of that stuff. We're just going to consider it going out the window and falling down to the ground. We are now moving the couch. That's what we would get for the work of gravity. Okay? 8,232 joules. All right? That's the work done by gravity if we were to do that. The work done by us getting it up there, we've got to do that same amount of work to get it up there. So work of us, if it's sitting down here in point 1 and we want it up here at point 2, for us, we would have to do that same amount of work, 8, 2, 3, 2, with the pulley system and whatever, and swing it in the window, or all that stuff. That's how much joules work it requires to lift the object up to that height. Fine, that's great. Now, let's step up here a little bit, and let's just talk about either way. Even if we were to go this direction, path 2, and we go up the stairs like so, all the way to the top, we have to do the same amount of work. Okay? It doesn't matter which path we take, as long as there's no friction. So this would be path 1, and path 2, same amount of work. So 1 and 2. This is all without friction. Okay? Now, let's add friction. Okay? So with friction, what are we going to do? Well, what would you rather do in a world with friction? In other words, the world in which we live in. Would you rather hoist it up on a pulley system and swing it in through the window? Or would you rather have your friend on one end of the couch, you on the other end of the couch, and then you take this practically dead body, 70 kilograms, up the stairs, bumping the walls and rubbing on the ground and doing all the stuff to get it up into position. Personally, I'd rather lift it up path 1 than path 2. Now, why is that? Because the work required in the real world for path 1 is less than that for path 2. Okay, so I don't know how much less. It all depends on how smooth you are at going backwards upstairs, and whether you need to lean on the walls or whatever you got to do. All those things are going to introduce friction into this situation, and that makes it difficult. So this is how you can tell that something is conservative or not conservative, right? It doesn't matter which path we take for gravity, it happens, okay? Gravity is going to be path independent. But for friction, it is path dependent, and you'd rather go in through the window than out, down, up and down the stairs with that dang couch. Okay, so Now, let's do a little, let's look at gravity with some path integrals. Okay, so I'm gonna erase this part. We're going to erase friction. And we're just going to do path integral with gravity, okay? Because gravity doesn't care which path we take. It still requires that much work to happen. So we're going to do a path integral. And what we're going to do is we're going to go from point 1 to point 2. So if I write out work 1 to 2, for path 1, that equals the integral over that path, so from 1 to 2, but I want to make sure that we know that we're taking path 1 here, so I'm going to stick a little 1 down there. And this is the force of gravity, and we're going to dot that force of gravity with dr. All right. Now, here's the point. That equals our 1 to 2 for path 2. 1 to 2 for path 2. All right, so here's what we're doing. We're going to start out at point 1. We're going to go in a circle. We're going to start out at point 1 and we're going to go this direction. Okay, we're going to go in a circle. So we're going to start at one point. We're going to end at that same point. So essentially, we're going to have to do work to get up. Gravity is going to do minus work to go up. So we're going to go up, let's see, we're going to go up path 2. So up, that's going to be minus this work of gravity that we figured out here. And then we're going to come back down path 1. That's going to be plus the work of gravity. So when we get our total work, 1, 2, 2, 1, all right, over both paths, we've got path 2 here, path 1 there. That really equals, and here's a new symbol probably for you guys, the force of gravity times dr. And that equals 0. Okay, so why does that equal 0? Well, because we are adding the work of 1, 2 for path 2 plus the work of 1, 2 path, well, I shouldn't say 1, 2, I should say 2, 1. In fact, no, this is the 2, 1. 2, 1. And this is 1, 2, path 1. And so that means that we are doing minus the work of gravity plus the work of gravity. And they're the same, right? So obviously it's going to equal 0. Okay, let's get back to this symbol right here. All right, so that symbol is called a, it's an integral symbol, we all know that, but it's a path integral. And path integral meaning a circular path. Okay, so we're starting at a certain point, we're going to another point, and it doesn't matter how we do it, okay, that is our circular integration path, okay? So we are starting at point 1. Let's erase this. We're starting at point 1, and we're going back to point 1, okay? So when a force is conservative, this integral is going to be 0, okay? Any conservative force, doesn't matter how you get or where those points are, you're going in this direction along your path. You're going to end up back at where you started, point 1, and you're going to get 0 work, okay, for that force, all right? But when we do work, we say it's work equals the force times the distance. Well, that work of gravity is the force of gravity only, right? We're not thinking about any other forces. If we're going to think about non-conservative forces or friction, NC for non-conservative, we're going to think about non-conservative forces. Well, that path integral for some non-conservative force, dr, is equal to, well, I should say not equal to 0, okay? Because it matters. Whichever path we take, we're going to go up one side and down the other. It's not going to give us 0 in the end, okay? We will be not getting our energy, our work energy back. Okay, so I think I did this one in class, so that's good. And we've talked about potential energy, so that's good. We've done the roller coaster, that's good, and we've done stability. So actually, I did a pretty good job, and I probably could have sealed this up last night, but I just was running out of juice, guys. I couldn't do it. So that is our little discussion on path dependent versus path independent. But anytime somebody says path dependent, you know that they're talking about a non-conservative force. And anytime somebody says it's a path independent force, you know that they're talking about a conservative force. And examples would be gravity, springs, electromagnetism. There's the strong and the weak force, and whatever. We don't need to talk about those because we're not going to work ever with those until we get to modern physics. So that's it. Thank you for your time. I'm going to upload this and get everything loaded so you guys have all the lecture you need. Okay.